Good.
For the most part.
So I got your email. Looks like we're going to look at Raleigh's theorem and the mean value theorem today.
Yes. I was going through the material she had provided, and there was nothing telling me what Rolle's theorem actually was.
Well,
I wasn't sure.
Okay. Rolle is an interesting character. First of all, he was a French mathematician, and he was one of the most vocal critics of calculus. He thought that it gave bad results and was based on unsound reasoning. So it's pretty ironic that one of the major theorems in calculus is named. Hold on a second. I can explain it to you real easily. If you have a function and that function goes from this point to that point, this being A, this being B, this is f of A, and this is f of B, right?
Yep.
What Raleigh's theorem says is that if this function is continuous and differentiable between A and B, and f of A is equal to f of B, like it is here, then there is some place in the interval where the derivative is equal to 0. Remember, the derivative is the slope of the tangent curve. So there's no way to avoid that point. It doesn't matter how the function looks. It can look like that. In this particular function, the bottom one, there's multiple places where the slope is equal to 0.
So it's telling us whether it's stating that in between these 2 points there is a relative max or a relative min?
Yes, essentially, yes. The mean value theorem was just included while we're talking about it. The mean value theorem says that if you have a function that is continuous and differentiable, and you took the average slope between f of A and f of B, in other words, f of B minus f of A, all divided by B minus A, that would be your average slope, rise over run,
Yeah.
that you are guaranteed to have a point on that function whose derivative is that same slope. In other words, if I look right about there, I can see that the tangent to that function is parallel to that average change. And that's what the mean value theorem says. And I read in my book, which I believe is the same book you have, because my exercises at the end of this chapter are the same as yours, which means you don't need to send this to me in the future.
Okay.
You can just tell me that it's, section 3.3. I have this book. I don't have the same additions, so the problems are slightly different. So there might be some cases where you might want to send it to me. But that's essentially Raleigh's theorem and mean value theorem. Okay? Now let's go through some of these problems. Do you want to just start with one and go forth?
Yes, that's always the best.
Okay. Explain why Raleigh's theorem does not apply to this function, even though there exists an A and a B such that f of A is equal to f of B. Well, this first one, the function is the absolute value of 1 over x on the interval, closed interval, minus 1 to 1. So first of all, where is f of a equal to f of b?
The endpoints of the interval one.
Yes, it's actually everywhere on the interval.
Yeah.
But definitely at the endpoints. And since we're looking at Rawls' theorem, that's what we're going to look at.
But
why does Rawls' theorem not apply here? Because clearly, if I plug in the endpoints, I get f of minus 1 is equal to f of 1. So f of a equals f of b. What is it about this function that makes Rawls' theorem not apply to it?
at x equals 0, it's undefined.
It's undefined, which means it's not continuous, which means it's not differentiable.
So,
About cotangent, cotangent of x over 2 on the closed interval pi to 3 pi.
because it's also not continuous.
Yeah, the cotangent curve has a asymptote at pi, and it is the inverse looking thing of the tangent curve, so it looks like that. And this is 0, so it has another asymptote at 2 pi. In other words, this is what the curve looks like. So in that interval between pi and 3 pi, right there at 2 pi, not continuous, not differentiable. Do you want to go through all of these, or it seems like...
I think the first 4 I understand.
The first 4 you understand. Okay, let's look at the second one. Find the x-intercepts of the function and show that f prime of x equals 0 at some point between the two intercepts. Factor that number 5 for me.
Factor. We get... So I'm just writing it down real quick so I can do it. I have issues visually.
Okay.
X minus 2 and x plus 1.
So that answers the first question. We can tell it's a quadratic. So its intercepts are 2 and minus 1. It opens up, so it looks something like this. And show that f prime of x equals 0 at some point between those intercepts. Well, we can see by looking at it that they're looking for this point right there.
Yeah.
How do we find that? How do we show? What is, first of all, f prime of x?
The derivative of the equation.
And what is it equal to?
The
derivative of this polynomial, that's the easiest way to do it.
We would get 2x minus 1.
Okay. And what if they want us to show is that that's equal to 0. So if I set that equal to 0, I get x equals 1/2. Which means at that point right there, where x is equal to 1/2, my derivative of that function has a slope of 0. Okay?
Yeah.
I don't want to go on until I feel like you understand what I'm saying. So I need a little bit of a clue. All right, number 6, the function is x times x minus 3 What are the zeros?
3 and 0.
What is f prime of x?
Is 2x minus 3.
And if I set f prime of x equal to 0, what is x equal to?
Which is 3 halves.
Okay. So we found the two x-intercepts, 0 and 3, and we found a point between 0 and 3 where f of x was equal to 0.
That makes sense.
Okay. So these are relatively easy. In other words, these are finding the zeros of these functions and then taking the derivative of these functions and seeing if you can solve it for x equals 0. 7 looks a little bit different. Let's do 7. Now, when I'm doing calculus, I'm always going to not write something as a radical, but I'm going to write it like that. Merely because if I have to take the derivative, I want it in this format, not with a radical sign. Okay, so what are the zeros here?
We have -4 and 0.
What's the first derivative of this function?
1/2 x. The inside is 1.
All right, let's go through the product rule. Product rule is uv prime plus u prime v, right? So let's do this one first. If u is x and v is x plus 4 to the 4. So we get x times, now let's take the derivative of that.
The inside.
Do the derivative of the outside first. Remember, it's the derivative of the outside times the derivative of the inside.
1/2 x. And then just 1.
Subtract 1 from the x.
Yeah.
And then multiply it by the derivative of the inside, which is just 1.
Yeah.
Okay? Plus this part here. U prime v, what is that?
That's just x plus 4 to the 1/2.
Now, our job is to see if there's any place where that's equal to 0. Well, let's see. Let's write this now in radical format. So let's see. We have 1/2 x all over the square root of x plus 4 plus the square root of x plus 4. Do that right? I think so. I can take this 1/2, stick the 2 in the denominator like that, set that equal to 0, and try to solve it. What's the first thing I can do?
Move the x plus 4 to the other side. The square root of x plus 4 to the other side.
Now?
Divide the whole thing by the denominator.
Multiply the whole thing by the
Oh,
denominator.
yeah.
Okay.
I got divide from.
So when I multiply the left by this denominator, what do I get?
2, -2.
Well, I have to multiply that by this also, which is x plus 4.
Yeah.
So I get -2 times the quantity x plus 4 on the left side of the equation equals x on the right side of the equation.
And then we distribute the -2.
Distribute that. Move the x on the other side. Is that in our interval? Oh, there wasn't any interval. I was thinking of the first 4 problems. Yeah, well that is the place where the derivative is equal to 0. In other words, the slope is equal to 0. That was just a little harder derivative to work out, that's all. Because we had to use the product rule. In other words, in 5 and 6, we could just multiply those out, and then the product rule, I didn't make the product rule, the power rule works great. But in 7, you can't use the power rule. You got to use the product rule in order to figure out the derivative and solve for where that derivative is equal to 0. So 8 is basically the same as 7. You have to use the product rule. You want to go through 8, or should we go on?
We should go on. I can go work through 8 by myself.
Yeah.
Watching this video.
I think so too. Yeah, you got the right idea how to work this. If you don't understand it now, you'll understand it when you go back and watch it the second time. Okay, in exercises 9 and 10, apply Rolle's theorem and find all values of c such that f prime of c equals 0 at some point between the labeled intercepts. All right, number 9 factors into x plus 3, x minus 1. So your intercepts are 1 and minus 3, as the graph shows. And what's the next step? Find the value of c. Rolle's theorem works because it's continuous and differentiable throughout that interval between the intercepts. So how do you get the value of c where the derivative is 0? In other words, how do we find that vertex?
We would differentiate the function and then set it equal to 0.
So what is f prime of x equal to?
2x plus 2. Oh, yeah.
So when I set that equal to 0, x is equal to minus 1. That is c, minus 1. And we can see in the curve that if we look at minus 1, go straight down, that indeed is where the slope of the tangent line is equal to 0. How about 10? First of all, does Rolle's theorem apply?
Yes. It is continuous and
differentiable. So n f of 0 equals f of pi. So there are 2 points. Same thing in the previous problem. F minus 3 was equal to f of 1. And that's why Rolle's theorem applies. And in 10, it looks like there's 2 places where the derivative is equal to 0. So what's the derivative of sine of 2x?
The cosine.
Times the derivative of the inside.
Times 2. So it's 2 cosine of 2x?
Uh-huh. In other words, let's talk about this. The inside is 2x.
Yes.
So f of x is equal to the sine of u. So f prime of x must be the derivative of the sine of u times du dx. So it's it's the derivative of the sine dx times du dx. This is the derivative of the outside, this is the derivative of the inside. Well, the derivative of the outside is just cosine of u, but the derivative of u is 2, so it's 2 times the cosine of 2x. So the cosine of 2x equals 0 where?
Cosine of 2x equal to 0 at pi over 4 and that's good. 3 pi over 4?
Yes. That's the cosine of x. Its zeros are pi over 2 and 3 pi over 2. So we would want to divide these by 2, so that x would be pi over 4. And that would give you the cosine of 2x would be the cosine of pi over 2, which is indeed 0. And 3 pi over 2, or that's another 0, so we would want to divide that by 2, and we get 3 pi over 4. Okay. Well, let's see, what else? 11 here? Blow this up a little bit. It's hard to- There we go. Is that okay? Can you read that?
Oh yeah, I have a copy of it on my screen too.
Alright, so this is pretty much the same exercise, except periodically Rolle's theorem might not apply. So does it apply on 11?
Yes.
Okay, and find value of c such that f of c is equal to 0.
So we would differentiate it.
F prime of x equal to?
Negative 2x plus 3.
So setting that equals 0 means minus 3 equals minus 2x, x equals positive 3 halves. And it's worth checking to make sure that is in the interval, 0 to 3.
Which it is.
Yes. It's going to be in all of these. Number 12.
It looks like it would apply again, so we just do the same thing. Differentiate and set it to 0.
You're going to have 2x minus 5. So x is going to be equal to 5 halves, and that is also in that interval. Number 13. How are we going to do number 13?
I would multiply the 3 together to get an equation and then differentiate it.
Yes. I mean, you could use the product rule, but I think it's probably easier to multiply the 3 together. Don't you?
Yeah.
When you start using the product rule on 3 things multiplied together, it gets quite hard.
More room for error.
Well, it's just hard to follow. I mean, you can do it because if you got A times B times C, you start out with A times B, and whatever that equals, that's times B. Product rule again. So,
I feel like
but
that would give me more room to make a mistake on.
yeah, for sure. Much easier to multiply these together. So let's do that. Let me watch you do it one time.
So we would get x squared, negative 2x, negative 1x, and then 2.
Plus 2.
Yeah, and then we would combine the x's before multiplying that. So we just have x squared. Yeah.
Okay.
And then we would go and we would have x cubed, negative 3x squared, minus another negative 3x squared,
Hold on. When you're multiplying these two together, are you doing it like this?
yes, and the x squared times the 3, so that's why I got my first negative 3x.
I gotcha. I'm with you now. I don't know what I was thinking. Okay, go ahead.
And then we would have we'd have 9x, positive 9x. And then on positive 2x, and then negative 5. And then just my
Negative
6.
6.
6. Yeah, I added them.
Okay.
And then
Now let's
just
combine
all
all the terms. Now we're
x squared, 6x squared, or negative 6x squared, and positive 11x.
okay. So that looks continuous. I don't see any places where there could be any asymptotes or anything, or discontinuities. So f prime of x.
We have 3x squared minus 12x plus 11.
Setting that equal to 0. It might be worth seeing if it factors one time, because there's only 2 factors of each of these coefficients before we resort to the quadratic. Signs have to be minus, minus, and the only thing that could possibly work is 11 and 1, and it doesn't work. Am I missing anything there? I don't think this factors.
I don't think it works either.
Okay, so what do we have to do to solve for it?
The quadratic formula.
Okay, so x is equal to
Negative b, so that's 12, or quadratic, negative b plus square root of quantity. Wow, but that's so long. Well, I have a little song there for us. Let me just sing it in my head real quick.
okay.
Quadratic. Plus or minus the square root of b squared, so b squared is 100 and, yeah, plus 4ac all over 2a.
Okay, so that's 144 minus 4 times 3 times 11 all over 6. Simplify that. Yeah, let's see, what do we got? 12 times 11, what is that? 132?
Yes.
144 minus 132 is square root of 12, which is 2 root 3.
Oh, 6. Then we could divide all the terms by 2?
Well, yeah, we could for sure do that. As to whether you need to separate this into 2 fractions or not, probably not. Since it's an irrational number, you can probably leave it in this form. If there was an I over here, then it would be very important to say that that was 2 plus or minus root 3 over 3i. Because when you're talking complex solutions, you want it in a plus bi format, always. So when you're using the quadratic formula, after you get the final answer, split it up into 2 fractions. That fraction and that fraction. If it's complex, you need to do that. If it's not complex, then there's nothing wrong with this answer here. Also would be correct to say that this is 2 plus or minus root 3 over 3. Take the I out of there. Okay? And then, of course, that's 2 different numbers that you could come up with. And that's going to be the value of C that gives you a 0 slope. Notice something about cubics as opposed to quadratics. Quadratics either going to look like that or like that. So there's only going to be one local extrema in a quadratic. Cubics tend to look like that. In other words, they're going to have 2 extrema. The number of extrema that a polynomial has is always 1 less than its degree of the polynomial. In other words, cubics have at most 2 extrema. Quartics have at most 3 extrema. Now, a cubic doesn't have to have 2 extrema. If I write the cubic function y equal x squared, y equal x cubed, there's a cubic function, and it doesn't have any extrema. It does have one point, I didn't quite draw it. It does have one point where the derivative is 0, right there, but that's it. That's not an extrema. So just because a function is a cubic doesn't mean it has to have 2 extrema. Alright. I think you get these, so we might not have to do all of these. Let's examine some that look different. Let's look at let's see, 14 is not much different than 13.
Yeah, no.
You're going to expand it out, produce a cubic polynomial, take the derivative of it, solve it. 15 looks a little different. Does Rawls' theorem apply on 15?
I think so.
Well, what is f of negative 8? First test for Rawls' theorem is, does f of negative 8 equal f of positive 8?
Pull up my calculator.
Do this one by hand. What is minus 8 to the 2/3 power?
2/3 power.
always take the bottom first. In other words, when you're taking something to the 2/3 power, that means you're taking that number, the cube root of it, and then you're going to square it. So what is the cube root of minus 8?
Is 2. Negative 2.
And then negative 2
and then negative 2
squared
squared
is 4.
4.
So that would be 4 minus 1 equals 3.
5.
And what about f of positive 8? Well, still 4 minus 1 equals 3, because 8 to the 2/3 is also positive 4. So it equals it. Question is it continuous? Well, let me bring up my Wolfram alpha here and let's plot that and see what it looks like. You familiar with Wolfram alpha? Have I talked to you about that?
No, you have not.
This is a nifty program. Better than your calculator. For one thing, when you put in a function, it immediately gives you feedback is the input. And a lot of times on your calculator, you can put in a function. If you get a parentheses wrong, you're not putting in the function you think you're putting in. So it's nice to have this input feedback. So we got what we were looking for. And they always give us the real and the imaginary part. Now the only part we're really interested in is the real part. And we're going from minus 8 to 8. Is there anywhere on that blue line that's not continuous or not differentiable?
It doesn't look like it.
It's certainly continuous everywhere.
At 0, it looks a little.
Well, at 0, what is the slope of that tangent line?
1.
It's vertical, isn't it?
Yeah, it is.
Vertical slope is undefined. It's infinity.
This is just not differentiable, though, then it Rolle's theorem doesn't apply.
Well, hold on a moment. We know functions are not differentiable where they're not continuous, and they're not differentiable at corners and cusps. Is this a corner cusp or not? Let's try to differentiate this function. See if it's differentiable there. What's the derivative? What is f of x? F prime of x?
2/3 x my negative 1/3.
Let's rewrite that. X goes in the bottom, and it's the cube root. Like that. So, if I try to set f prime of x equal to 0, does this have a solution?
I don't think so.
No, it doesn't. The only way a number is equal to 0 is if the numerator is equal to 0. There's no way this function can be equal to 0. It's also not defined at x equals 0. So the derivative is infinity. I would love to look this problem up in my book. Let me see it again. See if I have this one. This is 15. It's odd. My problems are a little different than yours. They switch them up on me. But 15 is the same. So chapter 3 to 15. 15, not differentiable at x equals 0. Is what it says. So Rawls' theorem cannot be applied.
Okay.
And in fact, if we look at that graph, there is no place how come f of minus 8 equals f of 8? You know what? I'm not sure that it does. What is minus 8 raised to the 2/3 power equal to? Minus 4. That's very interesting.
We got 4.
Well, how can it be minus 4? It doesn't matter whether you square it and take the cube root, or you take the cube root and square it. Either way, you get plus 4, don't you?
Well, yeah.
So how do they get
Because
4?
the cube root of a positive will be positive.
Right. Exactly.
Anything squared is positive.
Yeah.
I'm confused as well.
This isn't the first time I've been confused about this problem. I'm not sure why. I think it has to do with notation. Because clearly, if we take the cube root and then square it, we get plus 4. And if we square it first and take the cube root of that, we get plus 4. So I'm not quite sure where they get minus 4. But it changes everything, because if minus 4 is truly it, then we can't apply Rawls' theorem, because f of a isn't even equal to f of b. Not to mention the fact that it's not differentiable at 0. Let's leave that discussion to a later time, what minus 8 to the 2/3 power is. That's, I'm not sure about that one. Let's look at 16, which is different.
It has an absolute value in it.
Absolute value means what's there going to be in the graph.
Doesn't that make it a point where it's...
There's going to be a corner or a cut.
Yeah.
Okay.
I was sitting here with my hands doing a V trying to figure out what the name is.
Yeah, okay. Well, I could rewrite this as minus x minus 3 plus 3. So it is a reflection of the absolute value function translated 3 units to the right, raised up 3 units. So something like this. If I'm not mistaken, I think that's what it is. And on the interval 0 to 6, why does Rawls' theorem not apply here?
Because we have that corner.
Stuff is not differentiable at a corner.
Yeah.
We wouldn't know. I mean, how do you draw the tangents of that? You might assume the tangent is like that, but why? Why not the tangent being like that? So you can't really draw the tangent to a curve at a corner like that. So they're not differentiable at corners or cusps. 17. We factor the numerator. What do we get?
We would get x minus 3x plus 1. And
the denominator is x plus 2. That's is this differentiable over that interval?
Well, yeah.
Yes, it is. It's only not differentiable at x is minus 2. But that's
Which is
not in
outside
that
the
interval. Yeah.
Okay.
So we should be able to apply Rolle's theorem. Well, first of all, let's see, f of minus 1. Let's check that. F of minus 1 is 0. And f of 3 is 0.
No.
So f of minus 1 is equal to f of 3. So it's potential for Rolle's theorem. And it's continuous in that interval. So, yes, there's not even, when I first looked at it, I figured there was going to be a hole. In other words, this must factor into x minus 2 or some x plus 2, but it doesn't. So there are no points of discontinuity. We can apply Rolle's theorem. Now let's figure out how to figure out C.
Which
Oh.
step 1 would be differentiated, wouldn't it?
Differentiate it using the quotient rule. And it's going to be easiest to differentiate it if we don't factor it, I believe. One reason I factored it is I thought something was going to cancel out. So if that is f of x, what is f prime of x?
2x.
Hold on.
Well, first, we have to use the quotient rule, so it would be...
Right. What's the quotient rule?
It'll be g of x, h of x minus g prime x, h of x minus g of x, h prime x all over h of x squared.
Okay. So what's the first term I'm going to write?
G of x, which would g prime of x, which would be 2x minus 2. And then h of x, so x plus 2. And then minus g of x, so just x squared minus minus 2x minus 3.
Make sure you use these parentheses. Notice that if I omit them, I'm going to have a problem. Okay. No, I don't see much else that we can do other than expand that, combine like terms in the numerators, and see what we got. And then set it all equal to 0 and solve for it. Well, we can kind of see that as long as x isn't equal to minus 2, the only thing we really need to set equal to 0 is this, right?
Yeah.
So let's simplify the numerator.
So we would 2x squared, and then we'd get 4x, 2x, right? And then negative 4.
Okay. And then minus x squared plus 2x plus 3. So that we set to 0, and the reason I can ignore the denominator is the only way a fraction can be equal to 0 is if its numerator is equal to 0.
Mm-hmm.
This is the numerator, so what does this simplify to? We got x squared plus 4x minus 1. Obviously, we're going to have to use the quadratic, which will produce a positive or rather a real solution.
Yeah.
So, and I think we can see by now that that solution always falls in between those two endpoints. By Rolle's theorem, it has to. In other words, we could go through this, go through the quadratic again, look at our solution, and make sure that both of them fall in between that. That might be worth doing. Is it possible that one of them might fall outside that interval? I don't know. X is equal to minus 4 plus or minus 16 plus 4 all over 2. So that's equal to minus 4 plus or minus 2 root 5 all over 2. So that's equal to 2, 1. That's minus 2 plus or minus root 5. So minus 2 plus root 5 falls in that interval. That's a small positive number. Minus 2 minus root 5. That's outside the interval. Minus 4 and change.
Well, then only one of our solutions is in the interval. Only one of them matters for this question.
That's right. Interesting. I wouldn't have guessed that. I would have assumed that both solutions fell in that interval, but they don't. So there's only one solution that satisfies this problem, and that is minus 2 plus root 5. I got this one in my book. Let me just check that. Again, 3, 2. And this is problem 17. Minus 2 plus root 5. That's the only solution they show. In fact, their answer is f time of minus 2 plus root 5 equals 0. Alright, we only have a few minutes left. Chase, is there anything here you want to look at in our last few minutes that maybe what's your homework cover?
I think we're good.
Okay, so let's look at one more of these problems in this section. Now let's see, we did 17. 18 could be interesting, maybe. Let's see. X squared minus 1 over x. That's the same as x minus 1 over x. I don't know if that's helpful or not. And the interval is minus 1 to 1. Now, so when we plug in minus 1, we get 0. And when we plug in 1, we get 0. So f of a is equal to f of b. Can I apply Rolle's theorem to this?
Yes.
The function is not defined at 0.
At 0. Yeah, so no.
No. This function is not continuous even at 0, let alone differentiable. How about 19? We've done 19, we've done 20. Let's look at a harder. In other words, 19, clearly Rolle's theorem applies. Clearly there's 2 humps, or rather there's 2 right there and right there. So pi over 2 and 3 pi over 2 are going to be the 2 places where f of c is equal to 0. So that problem isn't hard. We have a hard one here. 21 looks kind of interesting. Let's take a look at 21 with our last 5 minutes. F of x is equal to 6x over pi. Don't be confused by the complexity of that. Pi is just a number. Minus 4 sine squared of x. Well, let's see. When x is 0, we got 0 minus 0. So f of 0 is equal to 0. F of pi over 6, that clearly is going to be equal to 0 also. That's 6 times 1/2 squared, which is 1/4, so that's let's see. Yeah, it's 1 minus 1. So that's equal to 0 also. So it fits the first part of Rolle's theorem. Is it continuous and differentiable everywhere?
I believe so.
Yes, it is. There's no place where there's any vertical asymptotes. We know this is differentiable and continuous throughout the whole number line. And that is also, pi is constant in the denominator, so we don't need to worry about it. So if we differentiate this, what do we get?
6 over pi minus 8 sine x cosine x?
Yes. So now we merely have to solve that. That's not the easiest thing to solve. Or is it? Let's see. We end up getting sine x cosine x equals 3 over 4 pi. See how I got that far?
Yes, I do.
Okay. And solving these trig functions can be quite challenging. There is a very nice way to solve this on your calculator. Do you know how to do it?
No, I do not.
Make y sub 1 equal sine x times cosine x. Make y sub 2 equal 3 over 4 pi. And wherever they intersect is the solution. Or I can do it on Wolfram alpha by saying sine x cosine x equals 3 divided by the quantity 4 times pi. And Wolfram alpha gives you the zeros also. Beautiful program. There's the functions, notice. There's the sine times the cosine. And there's 3 over 4 pi. So wherever those two graphs intersect, those are my solutions. It looks like minus 3. Well, whatever that number is. It shows me my zeros at the bottom there. Where are they? Solutions. Oh, they give them to us in that nice format. This is confusing. Let's see, what was our interval here? Our interval was 0 to pi over 6. So they only want the solutions. Pi over 6 is 0.5, a little bit more than 0.5. So this is the only solution they want right there. 0.2488. In other words, they want the solution where n equals to 0. You would get 0.2488.
Yeah.
I don't know of a real easy way to solve that algebraically. It's tough to solve trig functions when you have two different functions. We could perhaps do something by letting cosine equal the square root of minus sine squared and work with it like that, perhaps. I don't know. But as long as you're allowed to use a calculator in these problems, the easiest way to solve this is clearly using a calculator.
Yeah.
Okay. Well, I think that's going to do it for Rawls' theorem. We didn't get to use the mean value theorem. There aren't many problems that use the mean value theorem. The mean value theorem, actually, according to my book, the mean value theorem is called perhaps the most important theorem in all of calculus, as important as the fundamental theorem of calculus. And it's not such a seemingly amazing theorem. It's just that the mean value theorem is used to prove a lot of the other theorems that calculus uses. So that's what makes it so important. Remember, the mean value theorem says is that if you have a function continuous and differentiable, that the average rate of change between 2 points, there is going to be at least one point in that function whose derivative is parallel to that average rate of change. And in this case, there's two of them. That's what the mean value theorem says. All right. Chase, I will talk to you, let's see, Saturday, next Tuesday, or 2 o'clock next Saturday?
Yes, I believe so.
I will talk to you then.
Talk to you then.
All right, bye-bye.